What are phase diagrams, and how do they describe phase changes in a substance? Let's find out. But first, let's review our states or phases of matter. Our primary phases are solid, liquid, and gas. Solids are dense and rigid, holding their own shape. Liquids are also dense, but take the shape of their container. Gases are low density and take the shape and volume of their container. Going from a solid to a liquid is melting, and going from a liquid to a solid is freezing. Going from a liquid to a gas is vaporization or boiling, and going from a gas to a liquid is condensation. Going from a solid straight to a gas, skipping the liquid phase, is known as sublimation, and from a gas straight to a solid as deposition. Since each of these describes one phase turning into another, they are also called phase changes or phase transitions. Now, what phase a substance is in depends on its temperature and its pressure. A phase diagram is a map of that dependence made by plotting which phase exists for each combination of temperature and pressure. Let's consider the following phase diagram and label where each phase would go. If you can think of the molecular level and how each phase is structured, that can help you label a phase diagram. Solids, which are highly packed and frozen, exist under low temperature and high pressure in this region in the upper left. Gases, which have a lot of energy and have their molecules far apart and loosely packed, exist under low pressure conditions in this region at the bottom. And liquids, tightly packed but loosely bound, exist somewhere in between. But if that's not enough and you need a little more help, here's another way you can remember where everything goes. If we look at this plain diagram, what do we see? We see two cheeks, and what comes out of those cheeks? A little gas. Then, solids are frozen liquids, so solids will be the phase at the low temperature on the left, and liquids are melted solids, so they will be the phase at the higher temperature on the right. Now that we know what each of the regions are, let's look at the lines between them. These are where the phase changes actually occur. That is, they're equilibria lines where each phase that borders it exists together. For example, at this point, we would see both a solid and a liquid at that temperature and pressure. So, our phase diagram is telling us not only where our phases exist, but where our phase changes occur. For example, starting with a solid and changing the temperature until it becomes a liquid, we get melting as it crosses that line. And starting with a liquid and decreasing the temperature until it crosses that line, it becomes a solid, which would be freezing. Moving between the gas and liquid phases across their line would be vaporization and condensation, and between the solid and gas boundary would be sublimation and deposition. And we're not limited to changing temperature. We can achieve the same changes by increasing or decreasing the pressure instead. That is, instead of moving left to right, by moving up and down. When these transitions happen at 1 atmosphere, we call them normal. They are normally what we experience in our day-to-day. So, looking at 1 atmosphere and drawing a line across where it intersects the solid-liquid line would be our normal freezing point, and where it intersects our liquid-gas line would be our normal boiling point. We see here in the middle there's a point where all three of our phase boundaries intersect. That means that since all three phases are bordering on that point, all three phases can exist at that temperature and pressure. Since that's the case, we call that our triple point. Another point of interest is at the end of our gas-liquid line. While the solid-liquid line will continue indefinitely, this one ends, and it ends at what we call the critical point. Above this point, there is no distinction between the phases of liquid and gas, which is why the line disappears. So, the liquid phase spills over into this region, but so does the gas phase, meaning that in this region we have a new phase that we call a supercritical fluid, that is a fluid above the critical point. It has properties somewhere between a liquid and a gas. How do we use phase diagrams to predict phase changes? Let's practice. Let's say we have this phase diagram for carbon dioxide, and we want to know what happens if I have a solid at negative 35 degrees Celsius in 1 atmosphere, and then I raise its temperature to 25 degrees Celsius. Well, from my starting point, I move to the right until I get to 25 degrees Celsius on the temperature scale, and now I see it's in the vapor region, so what happened? It's sublimed. It's now a vapor. And we'll notice that this phase transition, sublimation, is happening below the triple point. And this is how dry ice works, right? Dry ice, which is solid carbon dioxide, is at 1 atmosphere of pressure, and as it heats up to room temperature, it starts to sublime, which is why we can use it for spooky theatrical fog effects. Now, what if I have a liquid at 25 degrees Celsius and 3 atmospheres? And this time, instead of changing the temperature, I want to change the pressure and increase it up to 5 atmospheres. Well, this time we travel up the y-axis for pressure, and we see that we end up in the solid region at 5 atmospheres. That means our liquid has frozen. So remember, there are two ways we can get a liquid to freeze. We can either lower the temperature, or we can increase the pressure. Our phase diagrams also allow us to see how temperature and pressure affect our phase transitions and when they occur. So for example, on our melting curve, we see that carbon dioxide melts just under 25 degrees Celsius at 3 atmospheres of pressure. But what would the melting point be at 5 atmospheres of pressure? Well, if we move that line up, we see that our new intersection with that phase transition is now just above 25 degrees Celsius. So at 5 atmospheres, it will melt just above 25 degrees Celsius. By increasing the pressure, we've increased the melting point temperature. Let's look at the phase diagram of water real quick now. We can find the normal freezing and boiling points that we're familiar with at 1 atmosphere, 0 degrees Celsius for freezing and 100 degrees Celsius for boiling. We can also notice something interesting about water if we look at its transition from solid to liquid as we increase pressure. Where our solid-liquid equilibrium line in our example with carbon dioxide had a positive slope, that is, it leaned forward, water's we see has a negative slope and it leans backwards. This means when I increase the pressure on solid ice, instead of saying solid, it melts. This is unusual. Where most substances freezing becomes more likely with increased pressure, with water, it actually becomes less likely. And that's it. That's how we can use phase diagrams to predict phase changes.